On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to talk about the intervals of concavity for this rational function right here. This is part 2. In part 1, we did cover the second derivative, where we started with the first derivative and then we found the second derivative, and then we ultimately ended up setting that second derivative equal to 0, and it turns out that value that we got for x actually ended up being a value of x that made the second derivative undefined. Notice this value here, x equals -3/2. If we take -3/2 and plug it into the second derivative, we do get a value there where we're dividing by 0, and obviously we cannot do that. And I've already created the number line here using that x value of -3/2, and let's go ahead and pick some test values just like we have done for intervals of increasing and decreasing, maximums, minimums, and we can also do the same thing for intervals of concavity. So a test value to the left of -3/2 would be -2, and a test value to the right of -3/2 will pick 0. Now this can get a little bit messy, especially with rational functions and second derivatives. You have to take -2 and plug it into this thing, and what we are concerned with is the sign of the second derivative. If it's positive, we have concave up. If it's negative, we have concave down. And this is no different than what we've done a while back with intervals of concavity for a cubic function. That's the statement here that I just said. If the second derivative is positive, then the function is concaving up. If the second derivative is negative, then the function is concaving down. So if you were to take -2 and plug it into this crazy function that we have here, the sign of f double prime would end up being a negative here. And I'm just going to save ourselves a little bit of time, but all I would do here is I would take -2, we'd plug it into all of this stuff, but you would get a negative number. So that implies our function is concave down. And there you have it right there. F of x is concave down for values of x less than -3/2. Repeating this process for 0, if you plug 0 into this function, you would end up getting a positive answer, which implies f of x is concave up. So therefore, f of x is concave up for values of x greater than -3/2. So therefore, listing our answers in interval notation, f of x is concave down from -infinity all the way up to -3/2. And we do not include -3/2. And f of x is concave up from -3/2 to +infinity. And now we can use Desmos here to check our work. So here's that same f of x function that we've talked about quite a bit now with maximums, minimums, intervals of increasing and decreasing, and now concavity. Here's that vertical asymptote for f of x, and it's also that spot that makes the second derivative undefined as well. Notice for all values of x less than -3/2, less than -1.5, this function is concave down over this entire interval. Whereas for values of x greater than -1.5 or greater than -3/2, the function is concave up, as you can see right there. Therefore, our solution, these intervals of concavity, are correct. And there you have it, the second derivative and concavity of a rational function. In future videos, we will explore exponential, logarithmic, and trigonometric functions as well. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.